Find the complex zeros of the given polynomial function, then write f in factored form as a product of linear factors. So let's circle here linear, so we know our factors have to be in the form x minus some constant. So we don't want any x squared factors or x cubed factors, they have to be linear. Okay, so from our steps, we know our first step, we want to look at the degree. So we have a degree 4 polynomial, so that tells us we're going to have exactly 4 complex zeros. And then corresponding to those zeros, that means 4 linear factors. So for each complex zero, we can make its corresponding linear factor x minus that zero. Okay, second step, we want to use the rational zeros theorem to list our possible rational zeros. So remember, we want to list the p and the q values. So remember, p is factors of the constant. In this case, we have 17. So we want plus or minus 1 and plus or minus 17. And then our q values are factors of our leading coefficient, which we can see is 1. So just plus or minus 1. And then all of the p over q combinations will be our possible rational zeros. So we want 1 over 1 and 17 over 1. So that's easy. Plus or minus 1, plus or minus 17. So these are our possible rational zeros. Remember, this doesn't tell us anything about the irrational ones, like square roots that we can't simplify, for instance. It doesn't tell us anything about those, but if they're rational, can be written as a fraction or whole numbers like these, it would be on this list. Okay, now we want to graph on the calculator to give us an idea of what this graph looks like. So here's our function, x to the fourth plus 6x squared, plus 6x cubed plus 2x squared minus 26x plus 17. Now, as far as the window, if you look at our function, we can see that our y-intercept is 17. You can see that because, to find a y-intercept, we put a 0 in for all the x values. Well, if you put a 0 in for all these x values, 0 to the fourth times 6 plus 6 times 0 cubed plus 2 times 0 squared minus 26 times 0, those all just go away to 0, and you're just left with 17. So that constant is actually our y-intercept. So that's a convenient way of finding our y-intercept of polynomial functions, the constant. So that's a hint then that when we pick our window, we need to at least go up to 17, and I'm going to go up at least twice that far and maybe even higher. I'm just estimating, just for example, I'm going to go up to 50 on the y-axis, just for example. Again, this is all trial and error when you're looking at the window here. And really we're looking at the calculator just to give us an idea of x-intercepts, not necessarily the exact shape or anything else specific about it, just an idea of the x-intercepts. So if I go to my graph, so I can see here, it looks like we have one x-intercept, and now we have total of 4 complex zeros, but only one x-intercept. So we know if the degree is greater than the number of x-intercepts, or if there's fewer x-intercepts than the degree, so we have degree 4 and we only see one x-intercept, remember that means that we've got to get back to a total of 4 zeros. So that means that we either have multiplicity, which we can see in this case because the graph touches and comes back up here at 1, we know that there is multiplicity, and or imaginary zeros. So remember, when the degree is larger than the number of x-intercepts, that means that we either have multiplicity and or imaginary zeros. So because it touches here, we know that there's multiplicity at 1, and you guys can go to the table just to verify that, or you could calculate the 0. So you can see that 1 is one of the zeros. So if we make just a little sketch just for our notes here, so again, the most important part is that 0 at 1. So we get that approximate shape. So what's most important is that it's touching there at 1 and coming back up. So if you want to write down the viewing window that we use, negative 10 to 10 on the x-axis with a scale of 1, and negative 10 to 50 on the y-axis with a scale of 2. Just an example of a effective viewing window. So if you want to note here that it touches the x-axis and doesn't cross, so that means we're going to have even multiplicity. So this means now we know that 1 is one of our zeros. So let's go through algebraically and verify that 1 is in fact one of the zeros. So we know if we divide our polynomial by the factor x minus 1, that'll verify that 1 is a 0. So remember, we put our 1 in the upper left corner and we list our coefficients of our dividend of our original polynomial: 1, 6, 2, negative 26, and then 17. So we perform our synthetic division, bring down the 1. 1 times 1 is 1. 6 plus 1 is 7. 7 times 1 is 7. 2 plus 7 is 9. 9 times 1 is 9. Negative 26 plus 9 is negative 17. And then negative 17 times 1 is negative 17. 17 and negative 17 give us 0. So we got a remainder of 0, so we verified that x minus 1 is a factor, which means that 1 is a 0. So let's break this down into factors. So we know that our original polynomial is the product of x minus 1, and our quotient, our depressed polynomial here, x cubed plus 7x squared plus 9x minus 17. Now, because we see that the graph touches at 1, that means we have even multiplicity. So that means we're actually going to count this 0, the 1, we're actually going to count it twice, because multiplicity means more than one. Even multiplicity means it has to be at least a multiplicity 2. So this x minus 1 actually appears as a factor twice. So we're going to divide by the x minus 1 again. So I'm going to put my 1 in the upper left corner, and I'm going to use the depressed polynomial. I'm now breaking down the cubic instead of the original. So I'll list my coefficients: 1, 7, 9, negative 17. So I'll bring down the 1. 1 times 1 is 1. 7 plus 1 is 8. 8 times 1 is 8. 9 plus 8 is 17. 17 times 1 is 17, plus negative 17 is 0. So we just verify that x minus 1 appears as a factor twice. So we can break down our polynomial further. We've got our x minus 1 from above. Then we just divided by another x minus 1. And when we did that, we broke it down. Here's our quotient: x squared plus 8x plus 17. So now we're down to a quadratic depressed polynomial, the answer from synthetic division. We got it down to a quadratic. So now we don't need to do any more synthetic division. We can use factoring or quadratic formula. So we can see that x squared plus 8x plus 17, that's not going to factor for us. So we can solve the equation. Actually, I'll move up over here. We can solve the equation x squared plus 8x plus 17 equals 0. We can just solve it directly to get the 0, set it to 0. So since it doesn't factor, we can use quadratic formula. So we want the opposite of 8 plus or minus square root 8 squared minus 4 times 1 times 17 over 2 times 1. So we can simplify here. So negative 8 plus or minus square root. So we've got 8 squared 64 minus 4 times 1 times 17 is 68. And then 2 times 1 is 2. So we've got negative 8 plus or minus square root of negative 4 over 2. And we remember our square root of negatives, that's where we get the imaginaries. So this is going to become negative 8 plus or minus 2i over 2. And we can reduce that, divide the negative 8 by 2 and get negative 4, and divide the 2i by 2 and get I. So this means our remaining two zeros are negative 4 plus I and negative 4 minus I. So then we can list all of our zeros. So we saw one of them from the graph, the 1, the x-intercept of 1, but it had multiplicity 2. You might want to indicate that. I think they asked you to do that in my math lab. And then we just found the remaining two imaginaries, -4 plus I and -4 minus I. And this makes sense that those remaining two zeros are imaginary because we couldn't see those on the graph. So if we look back up here at the top, we had a degree 4. We needed 4 complex zeros. We were able to see one of them on the graph. That's the x-intercept. That's the real one. But since it touched, we knew we had even multiplicity. So we actually divided by x minus 1 twice to verify that that x minus 1 was actually a squared factor. So in your list of zeros, you need a total of 4. This 1, because of the multiplicity, it's like it counts twice. Then you need your remaining 2 are imaginary, and they're imaginary. That makes sense because we couldn't see them on the graph. And then finally our factors, if we see that these are our last two zeros, then we can break this down into factors. So we have our x minus 1, and we can write that as x minus 1 squared, or just x minus 1, x minus 1. And now we can write, we'll use brackets because we're going to do x minus the entire complex 0. So if -4 plus I is a 0, x minus -4 plus I is a factor. And then if -4 minus I is a 0, x minus -4 minus I is a factor. And then we'll just want to go through and make that a little cleaner here. So we can distribute this negative through. So we distribute this negative, this becomes adding, and that's subtracting. So this will become x plus 4 minus I. And then here we'll distribute this negative, that becomes plus and plus. So this is x plus 4 plus I. So here's our polynomial f as a product of linear factors, so x to the first power factors. And here's our list of 4 zeros. 1, but it counts twice because that multiplicity, because we saw that it touched on the graph, and then our 2 remaining imaginary zeros.